Welcome everyone to Science to Sleep By. Tonight, we're going to slow down, breathe deeply, and drift into a quiet corner of the cosmos. This is Science to Sleep By, where we explore the mysteries of the universe in a calm, soothing way perfect for relaxing after a long day here in the United States, where the sky overhead connects us all to something far bigger, far older, and far more peaceful. As you settle in, let your mind float beyond the noise of daily life, beyond the traffic, the stress, the deadlines, and into a place where the stars drift silently and the planets follow ancient, graceful paths. Tonight, we're answering a simple but strangely comforting question. Why do planets orbit, instead of just floating away? So rest your head, breathe slowly, and let the science lull you towards sleep. Gravity is the quiet architect of the universe, the invisible force that shapes galaxies, forms stars, sculpts planets, and holds entire solar systems in their elegant, perpetual motion. When we ask why planets do not simply drift off into the infinite darkness of space, we are really asking about gravity, the most persistent and universal force in nature. To understand why planets orbit instead of floating away, we first need to understand what gravity truly is and how deeply it influences everything we see in the cosmos. Gravity is not simply a pull that drags objects toward each other, although that is how we experience it on Earth. In the deeper, more scientifically accurate sense, gravity is the curvature of spacetime itself. Every object with mass bends the space around it, and the more massive an object is, the more dramatically it warps this cosmic fabric. The Sun, holding almost all the mass of our solar system, creates a massive well in spacetime, a curved depression so deep that every planet, every asteroid, every particle of dust feels its influence. Planets follow the curves of this distortion, traveling naturally along the paths etched into the universe by the Sun's immense crescendo. Imagine this. Picture a heavy bowling ball placed at the center of a soft rubber sheet. The sheet sinks under the ball's weight, creating a large dip. Now imagine rolling smaller balls around the edge of this dip. They will naturally circle around the larger ball, not because they are being pulled directly toward it in the way we commonly visualize gravity, but because the shape of the surface guides them. Their path is curved because the space they move through is curved. This analogy, though simplified, captures the essence of Einstein's description of gravity, and it reveals something profound about why planets do not float away. They are moving along the natural pathways carved by the Sun's gravitational influence, and their continued motion keeps them from falling inward. Gravity is also remarkably consistent. It does not switch on and off. It does not weaken randomly. It flows outward from every mass, interacting with every other mass, shaping the cosmic dance with perfect reliability. In space, where there is no air resistance, no friction, and no physical barriers to slow an object down, gravity becomes the dominant force organizing motion. A planet in space is always in motion, and it always feels the pull of the Sun. These two conditions, motion and gravitational attraction, combine to create orbit. Without gravity, planet would indeed drift endlessly into the emptiness. Without motion, planet would be pulled straight into the Sun. But with both present, a stable path emerges, a delicate equilibrium that keeps planets circling in a balanced, eternal fall. Gravity also operates across enormous distances. Even though the planets are millions or even billions of miles from the Sun, the Sun's gravitational pull reaches them with unwavering certainty. The strength diminishes with distance, but it never drops to zero. The Earth, for example, is held by a gravitational pull that is strong enough to keep it tethered to the Sun's path, yet weak enough to allow it to move freely without being dragged inward. This balance is essential for orbit, and it highlights gravity's unique ability to act as both anchor and guide. It does not grab planets and hold them still. Instead, it shapes the space they travel through, ensuring their motion follows smooth, curved trajectories. What makes gravity even more fascinating is that it works in both directions. While the Sun pulls on Earth, Earth also pulls on the Sun, although the Sun barely moves because it is so much more massive. This mutual attraction is part of the universal law of gravitation described by Isaac Newton, who realized that every object in the universe exerts gravitational force on every other object. Newton's equations were groundbreaking because they revealed that the same force that makes an apple fall from a tree is the force that keeps the moon circling the Earth and the Earth circling the sun. This connection between everyday life and cosmic motion is one of the most elegantly simple truths in all of science. Gravity is universal, and it governs the small and the large with the same rules. Einstein expanded this understanding by showing that gravity is the geometry of spacetime, not merely a force acting across distance. His theory of general relativity did not replace Newton's laws, but enhanced them, giving us a more complete picture of how gravity operates. In Einstein's universe, objects follow the straightest paths possible through curved spacetime. A planet in orbit is not constantly adjusting its direction to circle the sun. Instead, it is following a natural path created by the sun's mass. The orbit is the result of the planet's inertia interacting with the sun's gravitational curvature. This means that orbits are not forced or artificial. They are the natural outcome of how mass shapes space and how objects move within that shaped space. Gravity determines not only that planet's orbit, but how they orbit. The speed of the planet, its distance from the sun, its mass, and the sun's mass all work together to set the exact shape and stability of its path. These paths can be nearly circular, slightly oval, or, in extreme cases, elongated or unstable. But in every case, gravity controls the boundaries. A planet cannot simply wander out of orbit unless acted upon by another large gravitational force. Likewise, it cannot drift randomly through space because the sun's gravitational field reaches far beyond the outer planets. Even at the edges of the solar system, the sun's influence shapes the motion of objects in the Oort cloud, a distant sphere of icy bodies surrounding our planetary family. When we look at planets through telescopes or in images from space probes, they seem serene, gliding silently through darkness. But their motion is the result of gravity's constant interaction, a quiet but firm guidance that has kept them in their paths for billions of years. Gravity has no sound, no color, no visible form, yet it orchestrates the structure of the universe itself. It binds solar systems together, shapes the orbits of moons, governs the tides on Earth, and holds galaxies in massive spirals. It is the reason planets remain near the sun instead of floating away into the endless black. It is the reason stars gather into clusters and galaxies form majestic shapes. It is the reason the universe has structure rather than chaos. Gravity is the foundational answer to why planets orbit instead of drifting off into space. It is the silent sculptor of cosmic motion, the steady hand behind the celestial choreography we observe across the night sky. Orbital motion is one of the most elegant and fascinating behaviors in the universe, a delicate equilibrium between a planet's forward velocity and the gravitational pull of the massive body it orbits. When we ask why planets do not simply fall into the sun or drift off into empty space, the answer lies in this perfect balance, a cosmic harmony that keeps worlds moving along stable, predictable paths. Understanding orbital motion requires us to slow down and visualize what is actually happening in the dark, frictionless expanse of space. A planet is not hovering in place, nor is it being pulled in a straight line toward the sun. Instead, it is continually falling toward the sun while also moving forward with enough speed to avoid ever hitting it. This ongoing fall creates an orbit, an unending curve that wraps around the sun like a dance choreographed billions of years ago. If we imagine standing on a high mountain and throwing a ball, it will eventually curve downward and fall to the ground because the Earth's gravity pulls it back. But if we could throw the ball fast enough, so fast that the curvature of the Earth drops away at the same rate that the ball falls, the ball would never land. It would keep circling the Earth indefinitely. This is the same principle that governs planetary orbits. The planets are moving sideways so quickly that even though gravity continually pulls them inward, they never reach the sun. Instead, they keep missing it, falling around it rather than into it. The forward momentum and gravitational pull work together to maintain a stable path in space. There is no air resistance to slow planets down. Once they begin moving, they keep moving. Their motion is determined not by friction or collisions, but by the gravitational fields they encounter. A planet's forward motion, often referred to as its tangential velocity, ensures that it does not simply succumb to the sun's pull. If a planet were moving more slowly, gravity would win and the planet would spiral inward. If it were moving faster, it would potentially escape the sun's influence altogether. Orbit exists in the sweet spot between these extremes. A precise velocity that matches the gravitational curvature of the sun's space-azimuth. Shape of an orbit is determined by a planet's speed and its distance from the sun. Most planets follow paths that are nearly circular but technically elliptical, as described by Johannes Kepler's laws of planetary motion. In an elliptical orbit, a planet moves faster when it is closer to the sun and slower when it is farther away. This variation in speed is not random, but perfectly consistent with the balance between gravity and motion. The sun's gravitational pull is stronger at closer distances, so the planet accelerates. As the planet moves away, the pull weakens, and the planet decelerates. This dynamic relationship maintains the orbit's shape and stability. Isaac Newton later expanded on Kepler's work by describing how a force acting on an object in motion creates a constant deviation from a straight line. Without gravity, a planet would move in a straight path indefinitely. But because the sun exerts a continuous gravitational force, the planet's path bends at every moment, curving around the sun. Newton illustrated this idea using the concept of uniform circular motion, showing that the inward force required to keep an object moving in a curve must be provided by gravity. This inward directed force is called centripetal force, and it is the reason planets remain in orbit. Einstein further deepened our understanding by showing that orbital motion is not merely a balance of forces, but the natural trajectory an object follows through curved spacetime. According to general relativity, the sun's mass creates a depression in the fabric of spacetime, and planets move along the curved paths within that depression. Their forward motion keeps them from spiraling inward, while the curvature keeps them from escaping. The orbit, therefore, is not forced, but natural, the result of how space itself is shaped. This interpretation makes orbital motion feel almost effortless, as though the planets are gliding on invisible tracks laid out by the geometry of the universe. Principle of forward motion and gravitational fall can also be seen in the behavior of satellites orbiting Earth. Like planets, satellites must travel at a very specific speed to stay in orbit. Too slow, and they fall back to Earth. Too fast, and they break free from Earth's gravity. The International Space Station, for example, orbits Earth at about 17,500 miles per hour. At this speed, it is constantly falling toward Earth while simultaneously moving forward quickly enough to keep missing it. This continuous fall creates a state of perpetual freefall known as microgravity, which astronauts experience as weightlessness. The same principle applies on a grander scale for planets orbiting stars. Orbital motion also explains why planets have stayed in their paths for billions of years. Without friction or significant external forces, their motion does not decay. They do not need constant energy input to maintain orbit. Instead, they move naturally along their trajectories, guided by gravity's steady pull. The stability of these orbits depends on the masses involved, the distances between objects, and the gravitational interactions with neighboring planets. While small perturbations can occur, the solar system is generally stable because each planet's orbit fits neatly within the gravitational structure of the system. The immense speed of planets is another key factor in orbital motion. Earth, for instance, travels around the sun at about 67,000 miles per hour. At this speed, it covers nearly 1.6 million miles every day. Mercury, being closer to the sun and feeling a stronger gravitational pull, moves even faster. The balance between speed and gravitational attraction determines not only the shape of an orbit, but its size. Planets farther from the sun move more slowly because the sun's pull is weaker at greater distances. This balance results in a beautifully ordered solar system, where each planet occupies a stable orbital region. The concept of orbital motion also extends beyond planets. Moons orbit planets, asteroids orbit the sun, and stars orbit the centers of galaxies. Everywhere in the universe, the same principles apply. Objects move forward, gravity pulls inward, and the resulting motion creates orbits. The universal consistency of these principles allows scientists to predict planetary positions decades, centuries, even millennia into the future. This predictability arises from the precise balance that defines orbital motion. Ultimately, orbital motion is a demonstration of nature's ability to create harmony through balance. It is a dynamic interplay between speed and gravitational fall, a constant negotiation between forward momentum and cosmic attraction. Planets orbit rather than float away because they are caught in this equilibrium, gliding forever along the curved paths carved into spacetime by the sun's immense percentile. Understand why planets orbit instead of floating away. We must look back not centuries, not millennia, but more than 4.6 billion years, to a time when our solar system was nothing more than a vast, cold, swirling cloud of gas and dust, drifting quietly in the Milky Way. This ancient cloud, called a solar nebula, stretched across trillions of miles, containing the raw ingredients that would one day become the sun. The planets, their moons, the asteroids, the comets, and even the dust beneath your feet. But none of these existed. Yet, everything familiar was still unformed, waiting for a spark, a collapse, a moment that would set the entire cosmic story into motion. And that moment came when something, perhaps a passing star, perhaps a shockwave from a distant supernova, disturbed the nebula, causing it to contract ever so slightly. That small change began a chain reaction that transformed a featureless cloud into a beautifully structured solar system filled with orbiting worlds. As the nebula began to collapse under its own gravity, it didn't simply fall inward in a straight line. Instead, like a spinning figure skater pulling their arms in, the cloud rotated faster as it shrank. This increase in rotational speed is a direct consequence of a principle called conservation of angular momentum, which states that when a spinning object contracts, it must spin faster to conserve its rotational energy. The same effect happens when a skater twirls, arms pulled in make the spin faster, arms extended, slow it down. In the early solar nebula, the immense cloud contracted over millions of years, gaining speed as it rotated. This rotation was the first step in shaping the orderly orbits we see today. As the rotation increased, the nebula flattened into a giant disk, like a cosmic pancake, stretching millions of miles across. At the center of this disk, material accumulated rapidly, forming a dense, hot core that would eventually ignite into the star we now call the Sun. Around this central mass, the remaining gas and dust continued spinning, drawn inward by gravity, but prevented from collapsing completely due to their sideways motion. This interplay between inward gravitational pull and outward rotational momentum created a stable, rotating disk. Within this disk, countless particles of dust and ice collided, stuck together, and grew. These collisions were gentle at first, microscopic grains clinging by electrostatic force. Over time, they formed pebbles, then boulders, then mountain-sized bodies called planetesimals. These planetesimals became the building blocks of planets, and their motion within the disk reflects the earliest beginnings of orbital behavior because the entire nebula was spinning. Everything within it inherited that rotation. The planets formed from material already moving in curved, circular paths around the sun, so once they grew large enough, they naturally continued along these inherited trajectories. This is the core reason planets orbit. They were born inside a rotating disk and retained the motion given to them by the formation of the solar system itself. If the nebula had not been spinning, if everything had collapsed perfectly straight inward, the outcome would have been completely different. Instead of orderly, stable orbits, the early solar system would have collapsed into a chaotic mass of material falling directly into the central star. But because the nebula rotated, and because angular momentum must be conserved, The planets formed in a flattened, spinning structure that naturally gave rise to orbiting worlds. As planetesimals grew into full-size planets, they began to clear their orbital neighborhoods of debris, either absorbing smaller bodies or flinging them outward with gravitational interactions. This process, known as planetary accretion, further strengthened the structure of the solar system. Each planet carved out its own band within the disk, establishing a stable region where it moved undisturbed by most other bodies. The stronger the gravitational influence of a growing planet, the more it could shape and sculpt its orbit. Gas giants like Jupiter and Saturn swept wide, powerful lanes through the disk, while smaller rocky planets like Earth and Mars created narrower paths closer to the Sun. These paths were not random, but aligned with the original rotation of the nebula. This inheritance of motion is why nearly all planets orbit in the same direction, and why their orbits lie roughly within the same flat plane known as the ecliptic plane. Heat played an important role in determining what kinds of planets formed where. Close to the newborn sun, temperatures soared high enough to evaporate volatile ices, leaving behind only metals and rocky materials. Farther out, the disk was cooler, allowing ices to condense and form massive cores that would eventually grow into gas giants. These differences in temperature shaped the mass and composition of planets and influenced how strongly gravity bound them into the early solar system. But regardless of size or composition, every planet formed within the same rotating environment, ensuring that each one inherited an orbital pattern defined by the ancient motion of the nebula. The formation of the Sun itself also influenced orbital motion. As the central mass grew, its gravitational pull increased, shaping the distribution of material within the disk. Regions where gas and dust were more densely packed produced stronger gravitational interactions, drawing in more material and accelerating planetary growth. This process refined the orbits even further, smoothing out irregularities and reinforcing stability. The Sun's gravity acted as the anchor of the system, ensuring that even as planets grew and moved, their orbits remained bound to its powerful gravitational well as millions of years passed. The solar wind, a continuous stream of charged particles flowing from the young sun, began to blow away the remaining gas in the disk. Once the gas was gone, the planets were essentially locked into their orbits. The structure of the solar system was now set. The planets continued moving along the curved paths they had inherited, and because space offers no friction or resistance, there was nothing to slow them down or alter their course significantly. These orbits became the long-term architecture of the solar system, enduring for billions of years. Everything from the asteroid belt to the icy edges of the Kuiper belt still reflects the original rotation of the solar nebula. What makes this process remarkable is how natural it all is. The planets did not need to be placed into orbit. Their orbits are not artificial constructs or delicate arrangements that could easily fall apart. Instead, they are the natural consequence of how the solar system formed. They move the way they do because they were born from a spinning cloud, shaped by gravity, guided by angular momentum, and sculpted by the evolving conditions of the early sun. Their motion is inherited, stable, and deeply rooted in the very origins of the solar system itself. Yet, as our understanding deepens, we begin to see a surprising truth. The same patterns that govern the largest structures in existence also shape the smallest. The spiral arms of galaxies mirror the twisting structure of hurricanes, which in turn echo the coiling of seashells and even the molecular geometry of life itself. This repetition of form and motion across different scales is what physicists and philosophers alike refer to as the fractal nature of the universe. And within that fractal order, one particular motion repeats endlessly. Rotation. From atoms to galaxies, the universe spins in self-similar harmony, each layer reflecting the motion of the next. The smallest building blocks of matter are themselves miniature worlds of rotation. Inside every atom, electrons dance around the nucleus, occupying shells defined not by physical orbits, but by probability zones of possibility where they might exist. While these electrons don't spin around the nucleus in the way planets circle a star, they still possess something we call intrinsic spin, quantum property that defines their magnetic nature, their charge interactions, and even their identity. This spin is fundamental. It is not caused by movement through space, but is woven into the fabric of what an electron is. Without it, the universe as we know it would not exist. The chemistry of life depends on spin. Magnetic fields depend on spin. The behavior of light itself depends on spin. Even in the quantum darkness, where particles blink in and out of existence, rotation is already there, encoded in the laws of nature. If we travel upward in scale, from the invisible to the visible, we find rotation again, only now expressed in the behavior of celestial bodies. A planet's rotation defines its day, its climate, and its seasons. The tilt of its axis determines the rhythm of sunlight and shadow that governs every living thing. The moon's synchronized rotation, always showing the same face to Earth, is another subtle expression of this cosmic rhythm. Its orbit and spin are locked together by tidal forces, showing how rotation links objects across space in a delicate gravitational dance. And beyond planets, stars themselves are massive spheres of plasma that rotate ceaselessly. Their spin helps distribute heat and energy, influences the formation of magnetic fields, and affects how they evolve and die. When stars are born from clouds of gas, their rotation is inherited from the angular momentum of the collapsing cloud. When they die, that spin can be compressed into something unimaginably fast, as in the case of neutron stars or black holes. A collapsing core can go from spinning once every few days to hundreds of times per second, conserving angular momentum and amplifying the cosmic pattern of motion. When we move even higher to galaxies, the pattern repeats again. Every spiral galaxy we observe is a masterpiece of rotation. The Milky Way, our own galactic home, turns like a vast wheel in space, its stars orbiting the center at hundreds of kilometers per second. One full revolution of our galaxy takes about 230 million years, yet the pattern of motion remains steady and elegant. The arms of the galaxy, rich with gas and dust, stretch out in spirals that mirror the swirls of hurricanes on Earth and the curves of water spiraling down a drain. The forces that shape them are different: gravity, pressure, angular momentum, but the geometry is the same. Across scales separated by billions of orders of magnitude, the universe repeats itself in form and motion. This fractal repetition tells us something profound about the unity of nature. It suggests that rotation is not a coincidence or a rare outcome, but a fundamental mode of organization. The same mathematics that describe the spin of an electron can, with modification, describe the orbit of a planet or the rotation of a galaxy. Patterns of rotation appear spontaneously whenever matter gathers, no matter the size of the system. It is as if the universe has one preferred rhythm, a kind of cosmic signature that repeats from the quantum scale to the cosmic web. The fractal nature of rotation also reveals how energy flows through the universe. In every rotating system, from atoms to galaxies, there exists balance, attention between inward pull and outward momentum. This balance prevents collapse and creates structure. In an atom, the attraction between electrons and the nucleus is countered by quantum motion. In a star, the inward pull of gravity is balanced by outward pressure and rotation. In a galaxy, billions of stars orbit the center in a perfect compromise between gravitational attraction and centrifugal motion. The result is stability through movement, an eternal balancing act that keeps the universe alive and structured. Even the largest structures in the cosmos, galaxy clusters and superclusters, display hints of this rotational symmetry. Astronomers have observed that galaxies are not randomly oriented. They often spin in coherent directions, suggesting that the primordial motion of the universe left a vast imprint of spin across billions of light years. Some theories even propose that the entire universe itself might possess a faint, large-scale rotation, so subtle that we can only detect its fingerprints in the cosmic microwave background. If this is true, then the universe's spin is not confined to objects within it, it is part of space-time itself. A feature of the cosmos on the grandest imaginable scale, this fractal echo of spin appears not only in matter, but also in patterns of energy and motion around us. Weather systems on Earth rotate because of the same fundamental laws that shape galaxies. The Coriolis effect, caused by Earth's rotation, gives rise to cyclones and trade winds that spiral across the planet. The fluid dynamics of air, water, and plasma all obey equations that produce vortices and spirals. Whether you are looking at a storm from space, a swirl of cream in your coffee, or the majestic turn of a nebula through a telescope, the same mathematical story unfolds: rotation as nature's preferred language of motion. To see this unity is to glimpse the architecture of reality itself. The universe is not random chaos scattered across scales. It is a self-similar system, where patterns of movement and structure repeat endlessly, each level reflecting the one above and below it. Rotation is the thread that ties it all together, a sign that the same principles apply everywhere, from the smallest particles to the largest galaxies. The fractal nature of spin is a reminder that everything in existence is connected through motion, that the dance of the cosmos is not many separate dances, but one infinite choreography, unfolding across every scale of reality at the deepest level of existence. Beneath the visible patterns of stars and galaxies, beneath even the atomic structure of matter, there exists a mysterious domain where motion, energy, and information blur together: the quantum realm. In this strange arena, rotation does not simply describe how things move through space. It defines how they exist in the first place. The concept of spin in quantum mechanics, while often explained as a kind of rotation, is not physical spinning in the everyday sense. Instead, it is a fundamental property of particles, a hidden axis of orientation that connects their internal geometry to the flow of time itself. The deeper we study quantum spin, the more we uncover that rotation is not just a physical action. It is the language through which reality expresses itself. Quantum spin is one of the most mysterious aspects of physics, because it defies visualization. An electron, for instance, can be thought of as having a spin of 1/2. This means that it behaves as though it must rotate twice 720 degrees before returning to its original quantum state. Nothing in the classical world behaves this way. You can spin a globe or a wheel once, and it looks the same again. But a quantum particle requires 2 full turns to be identical. This unusual property points to a deeper symmetry embedded in the structure of space-time, a symmetry that is topological rather than geometric, hinting that the universe itself has hidden dimensions of rotation beyond what we can perceive. In quantum field theory, every type of particle corresponds to a field that permeates all of space, and each of these fields possesses its own form of spin. Bosons, like photons or gluons, have integer spins, meaning they can align perfectly and form coherent states such as laser light or the strong nuclear force that binds quarks together. Fermions, like electrons or protons, have half-integer spins, which follow the Pauli exclusion principle. No two can occupy the same quantum state at once. This simple rule, born from the mathematics of spin, is what gives rise to all structure in the universe. Without it, atoms would collapse into featureless lumps of energy, and the diversity of matter would vanish. Spin, in this way, is not a detail of particle physics. It is the scaffolding of existence. The rotational symmetries of quantum mechanics extend into the very fabric of time. Every rotation, whether in space or in abstract quantum states, carries with it a phase, a hidden oscillation that defines how a particle evolves through time. When two particles interact, their spins intertwine, creating entangled states that share a single rotational phase across vast distances. This is why an action on one particle can instantaneously affect its partner, no matter how far apart they are. The rotational symmetry of quantum states, therefore, not limited to physical motion. It weaves together space, time, and information into one continuous geometry. Time itself might be understood as a kind of rotational phenomenon. In relativity, space and time are two sides of the same continuum, but their relationship can be described mathematically as a rotation between spatial and temporal dimensions. When something moves through space, Part of its motion is rotated into time. When it stands still, its motion through time dominates. This idea suggests that time is not linear, but cyclical, a dimension that turns continuously forward, much like a cosmic clockwork driven by the energy of the universe itself. If time has a rotational geometry, then every spin in the quantum world is not only a motion through space, but also a rhythm through time. This geometry becomes even more fascinating when viewed through the lens of quantum gravity and string theory. These frameworks propose that the smallest units of reality are not points, but vibrating loops or strings, each carrying angular momentum, a kind of spin at subatomic scales. The vibrations of these strings generate the particles we observe, while their rotations in extra dimensions determine the forces and interactions of the universe. Rotation, in this sense, is not something that happens within space-time. It creates space-time. The twisting and curling of these fundamental loops define the curvature of reality, the flow of energy, and even the passage of time. In the quantum vacuum, where particles flicker in and out of existence, spin continues to rule. Virtual particles, appearing for fractions of a second, always conserve angular momentum, the universal law of rotation that governs all interactions. This conservation law ensures balance at every level in an apparent emptiness. The vacuum is not still. It is a storm of rotational energy, a sea of spinning fields that underpin the solidity of the cosmos. When physicists talk about zero-point energy, the lowest possible energy state, they are referring to this restless rotational dance that never stops. Even when the universe is cold and empty, spin remains, whispering the rhythm of creation. The relationship between spin and magnetism further exposes the hidden geometry of the quantum world. The magnetic fields produced by electron spins are what make atoms bond, what make compasses point north, what allow planets to shield life from cosmic radiation. The magnetic polarity of the Earth, the sun's flares, and the spiral arms of galaxies all trace back to the same fundamental principle: rotating charge produces magnetic force. In this way, magnetism is the visible shadow of quantum spin on a cosmic scale, an echo of subatomic rotation projected into the macroscopic world. When we gaze into the night sky, we see an immense, silent panorama, stars glowing like eternal embers, planets drifting through the darkness, galaxies spiraling in elegant symmetry. But beneath that serene appearance, the universe is dancing. Every planet turns, every moon pirouettes, every galaxy whirls through space in a majestic rhythm of rotation. The cosmos is not still, it is alive with motion. Spin is not simply an outcome of physical laws. It is the unifying choreography that holds the universe together. From the smallest asteroid to the largest galaxy cluster, rotation governs balance, stability, and the very structure of the cosmos. Consider first the world beneath your feet. Earth rotates once every 24 hours, spinning steadily on its tilted axis. That rotation defines day and night, regulates temperature, drives the jet streams, and even influences the way life evolves. Without spin, the planet would be trapped in eternal daylight on one side and unending darkness on the other. The rotation generates a centrifugal balance that slightly flattens the poles and bulges the equator, creating the Earth's true shape, an oblate spheroid. But this rotation also gives rise to the Coriolis effect, bending winds and ocean currents, forming hurricanes and trade winds, guiding the global climate system that sustains life. Every cloud formation, every ocean wave, every gust of wind owes something to the spin of our world. Now expand that view outward to our solar system. Every planet, from the scorched surface of Mercury to the icy reaches of Neptune, carries the imprint of rotation. Each spins at its own pace. Jupiter in under 10 hours, Venus in 243 Earth days, Uranus rolling sideways like a cosmic barrel. These differences in rotation reveal the story of their formation, shaped by collisions, magnetic interactions, and gravitational tides. The angular momentum inherited from the solar nebula, that spinning cloud of gas and dust from which the sun and planets formed, ensures that each planet maintains its unique rhythm. Even the sun itself rotates, completing a turn roughly every 27 days near its equator. Its spin creates magnetic fields that twist and snap, generating solar flares and coronal mass ejections that ripple through the solar system and influence Earth's auroras and communication networks. Spin also determines the existence of moons and rings. The Earth's moon, tidally locked, spins at just the right speed to always show us the same face, a perfect synchronization born from billions of years of gravitational interplay. Saturn's rings, composed of ice and rock fragments, whirl in perfect balance, each particle maintaining its orbit through the delicate dance of centrifugal force and gravity. Another layer of stability comes from the gravitational hierarchy of the planets. Jupiter, being the largest, has a stabilizing effect on the solar system by capturing or deflecting comets and asteroids that might otherwise cause havoc. Some scientists even call Jupiter a cosmic shield because its enormous gravity acts like a guardian that protects inner planets from excessive bombardment. This role further preserves orbital stability by reducing the number of large objects that could perturb planetary motions. At the same time, Jupiter's gravity can also induce chaotic behavior in some smaller bodies, like comets or distant asteroids, but its influence on the major planets tends to promote long-term order. This gravitational hierarchy ensures that the largest forces are predictable and consistent, while smaller objects are too insignificant to disrupt planetary orbits in meaningful ways. The final factor that contributes to orbital stability is time itself. Because over billions of years, the solar system has already experienced its most chaotic era, known as the Late Heavy Bombardment, and survived countless gravitational rearrangements. What remains now is the result of natural selection on a cosmic scale, where only the most stable orbits have endured. Unstable planets or protoplanets were either ejected, collided, or absorbed long ago, leaving behind a configuration that has already been tested by cosmic turbulence. In other words, the solar system we live in is the stable remnant of a once chaotic environment, shaped by gravity into a delicate but reliable structure that persists across deep time. As we reach the quiet end of this journey through the mechanics of planetary motion, let your mind drift over everything we've explored. From the deep well of the sun's gravity to the elegant balance of speed and fall that creates an orbit, to the ancient spinning disk of the newborn solar system that set every world on its long, graceful path. We move through the invisible laws of angular momentum that keep planets gliding forward through the cosmic dark. And we stepped inside the delicate balance between stability and chaos that has shaped the solar system into the peaceful, predictable structure we see today. Together, these forces form a tapestry of motion that has lasted for billions of years. A cosmic choreography where each planet moves with purpose, harmony, and history woven into every mile of its orbit. And as you picture these planets drifting silently around our star, you can rest in the knowledge that their paths are steady, ancient, and endlessly patient, forming a celestial rhythm that continues whether we're watching or sleeping. A rhythm that reminds us that even in an ever-changing universe, some motions are beautifully stable and enduring.